Good morning, dear students. So, this is video lecture number 6, and in this video, we discussed about law of conservation of linear momentum. How momentum is conserved, and what is the application of conservation of linear momentum. So, one by one, I discussed all the things. So, open your notebook and write the heading. First heading, that is law of conservation of linear momentum. Linear momentum. Okay, law of conservation of linear momentum. So see, at any let at any instance two body having masses m1 and m2. Suppose two body having masses m1 and m2. Okay, both are moving with the velocity v1 and v2. So the momentum of the whole system, if we taking as both the two bodies as a system, so the momentum of the whole system equal to P1 vector plus P2 vector. Okay, this line is clear or not? Tell me. Now suppose F1 and F2 are two forces. F1 and F2 are two forces acting on particles of mass m1 and mass m2 respectively. Suppose F1 is acting on mass m1 and F2 is acting on mass m2. So the net momentum of the system will be changed. Let in a small time interval delta t, change produced by the force F1 and F2 are in M1 and M2 are delta P and delta P respectively. So we can write if force F1 is applied on M1 and F2 is applied on the M2. So there is net change in the momentum. So we can say delta P equal to delta P1 plus delta P. Okay, this line is clear or not? Then now if we divide all of 3 with delta t, so we can say that it is delta p upon delta t. This equal to delta p1 upon delta t plus delta p2 upon delta t. Okay, so delta p upon delta t is what? F external. Delta p upon delta t is what? F1, and delta p2 upon delta t2 is what? F2. So F external equal to F1 plus F2. So if there is no external force, if F external equal to 0, if F external equal to 0, that means delta P upon delta T is also 0. That means delta P equal to 0 and delta P equal to what? P final minus P initial equal to 0. So we can say P final equal to P initial. Okay, so if P final equal to P initial, that means momentum is conserved. So in the absence of an external force, the total momentum of a system remains constant. So we can easily say that in the absence of in the absence of An external force, the total momentum of a system remains constant, and does not change with time. And does not change with the time. Okay. So F external equal to 0, so P equal to constant. So what is the illustration? Like recoil of a gun. You can see what is the illustration. First part, recoil of a gun. Suppose bullet is fired in right direction. Suppose this is a gun. If bullet is moving in this direction, then recoil speed is in opposite direction to maintain the total momentum constant. Okay. Earth and the ball, jumping from a boat to the shore, flight of a rocket, explosion of a bomb. All are the examples of conservation of momentum. Okay, so write the examples: recoil of a gun. Second one, jumping from boat to the shore. If you jump from the boat, then you see boat will move backward direction. Third point, flight of a rocket. Fourth point, explosion of a bomb. So these are the main points: recoil of a gun, jumping from boat to the shore, flight of a rocket, and explosion of the bomb. So these are the examples of conservation of linear momentum. So conservation of linear momentum is clear to all of you. If there is no external force, so again I explain because this is very important concept. So see, in the absence of an external force, the total momentum of a system remains constant and does not change with time. There is no dependency on time. It is always constant with time if there is no external force. Okay. Once again, so that you understand. In the third line, you see you write delta P equal to P1 vector plus P2 vector. Okay. And we know delta P upon delta T equal to delta P1 upon delta T1, delta T plus delta P2 upon delta T. So this is F1 and this is F2. F1 contains external and internal both. So we can write F1 external plus F1 internal, and F2 is same, F2 external plus F2 internal. So we can write F1 external plus F2 external in one bracket and F1 internal plus F2 internal in one bracket. So we know that F1 and F2 internal, they form action reaction force. F1 internal plus F2 internal, they form action reaction force. So F1 internal equal to minus F2 internal. So F1 internal plus F2 internal equal to 0. Okay, so this bracket becomes 0. So we are only left with a bracket F1 external plus F2 external plus 0, and this is equal to the F external. So we can easily write F external equal to delta P upon delta T. Okay. So if F external equal to 0, then delta P equal to 0, and remaining is the proving thing. Okay. So conservation of linear momentum is clear to all of you. Okay, students. Bye bye. Take care all of you.